Hello guys, I hope y'all had a great weekend. So last Friday we started talking about factoring. We did some examples and I gave you a flowchart to go through. And today I'm going to talk about two special cases that we didn't cover on Friday where the flowchart might not work all the time. So we do have perfect squares here, and I just want to fix this. This is supposed to be a subtraction sign. It's fixed on yours. On your notes, I already fixed it, but on mine it's not. So, again, this page right here is if you open up the journal slides that we copied from last week, I've added this as a third slide, so you just need to copy that last slide over. You don't need to copy all three slides, okay? So this is that third slide. And today we're adding perfect squares. So if it's written in one of these two formats, then we can rewrite it in one of these two formats. And then we also have prime polynomials. So if we have a prime polynomial, this means it can't be factored anymore. So like we have a prime number 3 or 5, the only thing that these two factor down to are 1 in itself, right? This is what prime numbers look like. So we have the same thing when it comes to polynomials, where we have cases where the polynomial just won't factor anymore to give us real solutions. So we'll have polynomials that won't factor to give real roots, and what this means is if I were to graph these polynomials, they wouldn't cross the x-axis. So we will solve these quadratics in the future. Like I said, here in Unit 4, we'll solve them, and we'll start talking about complex solutions and complex roots. But for right now, I just want to say these are non-factorable, and we're going to call them prime polynomials, okay? So for example, number 1, we have 9r squared minus 5r minus 10. So if I think about my x, then I'm looking for something that multiplies to give me negative 90, but when I add it, it gives me negative 5. So I'm going to start out by, I'm just going to think about I'm going to think about the factors of negative 90. Well, there's 1 and 90, 2 and 45, 3 and 30, 5 and 18, 6 and 15, and 9 and 10. So if I'm looking at these, no matter which way I subtract them, I'm going to end up with 1 left over here and 9 left over here. And then those numbers are just going to keep getting bigger as I move up. So I don't have two numbers that give me a difference of this negative 5. So for this situation, I'm going to say this is not factorable and it's a prime polynomial. It's prime. And that's it. I'm going to be done on that problem. So if I can't go through my flowchart, so I don't have a greatest common factor here, I can't figure out what these two numbers would be, then I'm going to say it's prime, and that's all I'm going to do with those for right now. Like I said, as we move throughout the year, we will use the quadratic formula and we'll actually solve these and figure out those complex roots. But for right now, we're just going to say they're prime, okay? And in some cases, that's all we'll need to do. All right, so let's look at number 2. We have r squared plus 6r plus 9. So if I look at my flowchart, I don't have a greatest common factor, and I have two positives, so I'm looking at this right here. So I'm going to have a plus and a plus. So eventually this will look like r plus something times r plus something, right? I'm looking for two numbers that multiply to give me 9 and add up to give me 6. So two numbers that multiply to give me positive 9 and add up to give me positive 6. I'm going to say that's 3 and 3. So this was pretty easy to use our flowchart for, but we also can use this perfect squares concept here as well, because r plus 3 times r plus 3 is the same thing as r plus 3 squared. So if we look at this top example here, where we have it says if we're written in x squared plus 2xy plus y squared, then it will equal x plus y squared. So if I'm looking at this here, r is my x, so I do have r squared. And then I want to rewrite this as 2xy. Well, r is my x value, and then I just need to figure out what my y value is. Well, if my last term here is y squared, I can rewrite that as 3 squared. So then I'd have this 3 here, and if I'm multiplying these things, right? And if I multiplied 2 times 3, I'd end up with this 6. So I can rewrite this in the form of x squared plus 2xy plus y squared equals x plus y squared, and get there, right? It's a little bit easier to think about it the original way, using the flowchart, but we can also kind of see that we're multiplying by r and 3 here, and 2 times 3 would give me that 6. So let's look at a little bit more difficult problem here. We have 80p squared plus 200p plus 125. So first I'm going to look and think, is it this yet? Well, these are all pretty large numbers. They have, like, 2 of them end in 0, 1 of them end in 5. So my initial thought is going to be check to see if 5 goes into all of these numbers. So we know, obviously 5 goes into all of them. So I'm going to see if I divide each of them by 5 and take a 5 out, if that would be my greatest common factor. So that's going to leave me with 16p squared plus 40p plus 25, right? Yeah. And 16 and 40 are even, and then we have 25. So I think this is all I can take out of these. So now, keeping in mind this perfect squares format, I'm looking, my main concern is this term and this term. So what is my x and what is my y? My last term here is a perfect square. It's 25, right? 5 times 5 is 25. So I'm going to immediately think about these perfect squares and see if I can rewrite it using that format. So if I can identify x squared, well, if I can rewrite this first term with a square, and I think I think the square root of 16 is 4, and then I can say p and square both of those, right? That would give me, if I, these two things are equal. 16p squared is equal to 4p squared. And then the square root of 25 is 5. And I think this will work, right? So if I have 4p squared, if I do 5 times 4p plus 5 and square that, well, if I write this back out, let's check our work here. Then 4p times 4p would give me 16p squared. 4p times 5 is plus 20p. Then I'd have another 20p. Then I'd have a 25. Well, if I combine these two terms here, then that's going to give me right back to what I needed. So when you're thinking about these perfect squares, if you look at your first term and your last term, and they both have perfect squares, we can rewrite them. Like this first term we could rewrite as a perfect square. Then it gets you pretty easily to that format. This comes with practice, right? So you have to kind of build this mindset of looking for these perfect squares. Just like up here on our flow chart with our two terms, we're looking for these differences of squares or these differences of cubes. We have to memorize what these cubes and squares are so that we recognize them and they make our lives easier, right? So when we see those, then those would be kind of my first thought. If I see a perfect square somewhere, I'm going to think immediately, go to these perfect squares format. And then if I can't use those, then I'll go through my flow chart and see if there's other things I can do. So I've posted an assignment. You should be able to do part of the assignments there. We will start solving tomorrow, so we'll be able to finish up that assignment tomorrow. But that's what I want you guys to work on today, is going through that assignment. And let me know if you have any questions.